Wow, look at that. All right. So sorry, I'm running just a few minutes behind. I was clearing out all of the WebAssign extension requests. So if you requested an extension on homework 1, that has been granted now. Homework 2 will be coming out today, and of course will be due next Monday following that same pattern. Let me get my screen share set up, and we can switch over to the .cam and start on today's material. This is section 4 of MAC 1140. It is a lecture, and today is the 31st. Today I'll begin with any homework questions. I want to make sure we've buttoned up anything there. And then we're going to begin talking about section 2.3, and we may get into 2.4 today. Those are the two sections for this week. And that's the plan, right? So the rule for homework extensions, in case you're wondering, in case I haven't made that explicit enough, if you ever need more time on the homework, just submit an extension request in WebAssign. Every day I'll go in and check for extension requests, and I'll just grant them. You don't need to explain why. I understand this is life. You are all adults. It's your responsibility to stay caught up with the homework. But if you fall a little bit behind, it's not the end of the world. I'm not going to judge you for it. Just submit a request, and I'll usually extend it through for a full week to the following Monday. So are there any questions from homework 1 that you guys would like to talk about? Anything that has had you stuck or puzzled or bothered? Maybe you got it, but you're not 100% happy with how you got there. Anything like that.
I do have a question, but the thing is I did it like 3 days ago and I don't remember.
Well, let me pull up the homework here and I'll scroll through it. You stop me when you see the one. All right. So yeah, go ahead and stop me when you see the guy that you're thinking of.
I think it was 12.
Okay. Yeah, there is a term here that we haven't talked about yet, and that's net change. So I apologize that that snuck in there. So let's take a look at number 12. Are there any other problems from the first homework that you guys would like to see, discuss, anything? You can type it in chat or you can hold down spacebar to talk. Lainey, could I ask you to be a little more explicit? In one of these piecewise guys. Let's see, I think we had, yeah, some graphing problems down here, number 47. 30 and 47, okay. All right, so let's do those. I'll go through them in order. We can do one more of the A+H things. We actually did a few of those last week, so I would encourage you to go back and look at those from our videos last week. Last few questions. Yeah, graphing these piecewise functions. So we'll do 47. That's an example of one of those. What else didn't we do? I think we did that. Yeah, okay. So let's start with this list. And then there's one here, one of these A+H guys. I'll throw 29 in here also. All right, we're gonna need to move kind of quick. So number 12 does require knowing this definition that we haven't talked about. and I apologize. You can get it from the textbook, of course, but here, f of x, let me write this down. I should not leave that to you to do. I should always explain these things. You want to find value at x equals -1, at x equals 3, and net change from x equals -1 to 3. Okay. So net change, right? I think the first two parts of this, most people would not struggle with too much. I have no idea who that is. Maybe I do. I'll have to call them back. Each of these guys, you're just going to evaluate the function there. So remember, the value of the function at a given input is the output of the function when you plug in that input. So for part A, the value of f when x equals -1, that is f of -1. And f of -1 is what I get when I substitute -1 in for x. So that would be -1 cubed plus 1. -1 cubed is -1 times -1 times -1, which is -1. So this is -1 plus 1, which is 0. Part B asks for the value of f when x is equal to 3, that is f of 3. So the value of the function is the output. That's what you get when you plug in the corresponding input. So here that would be 3 cubed plus 1. And 3 cubed is 3 times 3 times 3. That's 9 times 3 is 27. So 27 plus 1 is 28. And the net change, for a function f between or from x equals a to x equals b is you might know this term net from elsewhere in life. When we talk about net, we mean overall. So like, what is the overall change in the function's value from the input A to the input B? It's just f of B minus f of A. So whatever else went on, however wiggling up and down we did, we want to know how high are we at the end compared to at the start? Or what's the height of f at A compared to the height of f at B? So we always define that to be f of B minus f of A. Here B is the number, right? So between -1 and +3 is the larger number. So for part C here, the net change for f from x equals -1 to x equals +3 is f of 3 minus f of -1. And conveniently, those are two things that we calculated just a minute ago. F of 3 is 28, f of -1 is 0, so this is 28 minus 0, or 28. And the picture for net change is like this. If I've got A here and B here, then the net change.
Could you scroll down a tad?
Sure, yes. Then the net change here, this is f of A, this is f of B, is just this distance. And it's positive if you're going uphill overall. It's negative if you're going downhill overall. All right, so here in the picture as I've drawn it, the net change would be negative. For our function, the net change here was positive, because f of 3 is bigger than f of -1. So this was number 12. You want to compute those two function values, and then you just subtract them in the appropriate order to get the net change. Like I said, we are going to have to move kind of quickly through here. Are there any questions
Thank you.
you want to have on this? Okay, so I think if we're going in order, 29 was the next one that people wanted to see. So let's take a look at 29, and we'll do 30 and 47. So 29 is one of these difference quotient things. F of x here was, and your numbers might be a little bit different because WebAssign generates those randomly, but I've got 4 over x plus 9. We want to find f of a plus h, and the difference quotient, f of a plus h minus f of a all over h. So this really comes down to how well you understand function notation. We talked about that last time. 6e. Okay, I see 6e requested there as well. I'll try to go back to that. We have to make sure we understand what these two objects are, and then we can use them to build this object. And then we'll work with this until we have it as simplified as we possibly can get it. So remember, f of anything is what you get by taking the formula for f of x and swapping in that thing for x. And we always do so in parentheses because it can really make a difference sometimes. So f of a is 4 over a plus 9. F of a plus h is 4 over a plus h plus 9. And that does happen to be the same as 4 over a plus h plus 9 without any parens, because there aren't any numbers multiplying here, any powers here that we need to worry about. For being very careful, I should write this a in parens also, and we could say that's the same as 4 over a plus 9. But you should always start with these parentheses, because they really can make a big difference. So that's the first two parts. And then out of these, we build the difference quotient, f of a plus h minus f of a all over h. F of a plus h, this first piece, is this guy. So that's 4 over a plus h plus 9. And from that, we want to subtract this guy, which is 4 over a plus 9. And then we need to divide everything by h. My first step here is to rewrite this big divide by h as a multiply by 1 over h. That keeps us from having to write those huge, long, annoying fraction bars. And then what's left in the parens there is just the numerator, 4 over a plus h plus 9 minus 4 over a plus 9. And my goal is to get to a place where I can cancel this h from the bottom. If I'm going to do any work with these, I need to put these two fractions together. I need to have a common denominator. And since this denominator is a plus 9, and this denominator is a plus h plus 9, the only reasonable common denominator to use is this times this. So my difference quotient is equal to 1 over h times the 4 over a plus h plus 9. I'm going to multiply him by a plus 9 over a plus 9. And that will give him the denominator I'm shooting for. From that, I'm going to subtract the 4 over a plus 9 times, he gets multiplied by a plus h plus 9 over a plus h plus 9. And now when I multiply these out, these two will have the same denominator because they have the same two factors. We don't actually need to multiply the denominator all the way out. We can leave it as it is. But we do need to multiply out the numerators. And remember, we need to be thinking of these all as in parens because these fractions are grouping symbols. So this will be 4 times a plus 9 minus 4 times a plus h plus 9 all over that common denominator of a plus h plus 9 times a plus 9. So the steps here are, make sure you find these guys correctly. Then plug each of them into the corresponding part of this formula. So here's f of a plus h minus f of a. And then from there, you just need to do quite a bit of algebra. All right, dividing by h is the same as multiplying by 1 over h. That's how I like to write it. You don't have to write it that way. You can continue writing this big long fraction bar if you want. I just don't like doing that. I find it a little bit inefficient use of space and kind of just annoying to write a big long fraction bar. And then we need to combine these into a single fraction. So we have to have a common denominator. Since these denominators are made up of variable quantities, they've got a's and h's in them. I can't do any like nice arithmetic. The only way to combine those is to use the product of their denominators. So each guy gets the piece his denominator was missing. This piece was missing the a plus 9 factor downstairs. So I multiply him by a plus 9 over a plus 9. And that will give him this common denominator. This piece is missing the a plus h plus 9 factor downstairs. So I multiply him top and bottom by a plus h plus 9. And now that they both have this same denominator here and here, I can write it as one fraction over that denominator with the tops subtracted. It's important that we use these parentheses here because this 4 needs to be distributed. This 4 needs to be distributed. But as long as you've done everything correct up to here, the rest is pretty straightforward. This will be 4a plus 4 times 9. 4a is just 4a, and 4 times 9 is 36. And then I distribute the negative and the 4 here. That's important, right? This minus and the 4 get distributed. So I'll have minus 4a minus 4h minus 36. And all of that is being divided by this common denominator still, a plus h plus 9 times a plus 9. Once we've distributed everything, you'll see there's quite a bit of cancellation. The 36's go, the 4a's go, and we get 1 over h times negative 4h, all divided by a plus h plus 9 times a plus 9. And then you could write that as a single fraction. Of course, we multiply fractions straight across. That's negative 4h over h times a plus h plus 9 times a plus 9. And notice that I never FOILed out or distributed out that denominator. There's no reason to ever do that. The denominator, leave it factored. Leave it factored. Because the only thing I want to cancel is the h. So this will become negative 4 over a plus h plus 9 times a plus 9, like this. And that is your fully simplified difference quotient. These are very important problems. We're going to be seeing this difference quotient pop up again and again throughout the class, not just in the sections we're working on last week, but the stuff we're working on this week and the stuff we'll be working on down the line. So this procedure is super duper important. So I'd like to take a second to answer any questions anybody has about what we're doing here, why we're doing it, why it works that way, any of that stuff. Questions on where these factors came from, why I introduced them here? Or how those combine into this? That's really where the challenges lie in this problem, I think. Okay then, if everybody is genuinely comfortable, we'll move on. Number 30 was next. Let's see, this is really the same thing, isn't it? Yeah, sorry, so I'm not gonna do this. So we can't afford to burn too much class time. 29, 30, really the same thing. It's just you've got an X up here as well as down here now. So run precisely the same procedure for 30 as you run for 29 and you'll be okay. 47 was next then. Which I think is that the very last one. It is, yeah. Okay, so this is gonna be 47, and they give us a graph. They tell us it's piecewise, and they ask us to come up with the formula. That's an interesting challenge. So here's -1 and -1. We've got a point here. There's +1 and +1. We've got a point here. We've got a straight line segment joining those 2 points, and then 2 horizontal line segments running off forever and ever this way and forever and ever this way. And they want us to find a formula for the piecewise function. F of x. All right. So what I see when I look at this is 3 pieces. I see what looks like one function here, what looks like one function here, and what looks like a third function here. Right? This is a constant function whose value is always 1. So this line segment is just y equals 1. Similarly, this line segment down here is also a constant function. It's a horizontal line. It's just the line y equals -1. And then this linear piece that's in between, well, let's see, the slope there, if you calculate this rise over run, between this point and this point, the rise is 2, the run is 2. So this piece here is a linear function with slope 1 and y-intercept 0. So this piece is y equals x. Those are our 3 pieces. My function behaves like y equals -1 for all of these x values over here. That's for all the x values that are less than -1. So I'm going to split my function up according to the places where the behavior changes. F of x is piecewise 3 different things. It behaves one way if x is less than -1. It behaves a different way if -1 is less than or equal to x is less than or equal to 1. And it behaves a third way if x is greater than +1. X is less than -1, that's everything to the left of -1. And for that piece, my function behaves like the constant function y equals -1. So I would say f of x is equal to -1 if x is less than -1. Between -1 and +1, f of x behaves like the function y equals x. So f of x is equal to x if x is between -1 and +1. And to the right of 1, f of x is equal to the constant function +1. So this would be the formula for that piecewise function. Yeah, as long as you're sure that this is linear, and here we are because it's a straight line, you can calculate the slope and the y-intercept and that will work just fine. This piece in the middle here could have been quadratic or something. It could have been curvier. And then you would have to use whatever you remember from college algebra to find the equation for a parabola. You know, we could use whatever pieces we want here, but we're trying to be nice by using piecewise linear functions. So yeah, what Lily said is correct. We would use mx plus b to help us figure out what formula to apply in this middle piece. I'm okay with spending a second longer here if we want to, because I know piecewise functions are kind of intimidating and kind of new. So are there any other questions about this guy? Questions on piecewise functions in general? Somebody else said something about just graphing functions. Would we be okay with going from this formula to this picture rather than the other way around? Everybody comfy with how you would get, if I gave you this formula, we could all draw this graph? Okay. If there are other questions that you guys want to ask, I know that this stuff is intimidating. Refer back to our previous videos, right? They're all up on YouTube. They're even in a nice ordered playlist there on my YouTube channel. So you can rewatch some of the previous videos where we did a lot of other piecewise graphing. I think every day last week, both Monday and Wednesday of last week, we did a bunch of piecewise graphing. So take a look at those for more help with this stuff if this is still feeling a little bit weird to you. The other question we wanted to look at was number 6E. That one slid in at the end. So we'll take a look at that.
Sorry, it was kind of like an easier one, but it was a little confusing when I read it.
That's
So
all right,
I
not too bad. Yeah, no, there's nothing to stress about here. So we can talk through this. X is positive means X is greater than 0. T is less than 6 means T is less than 6. And A is greater than or equal to pi. I think each of those is pretty straightforward. So I'll write them down here. X being positive means it's greater than 0. So we would write the inequality X is greater than 0 for X is positive. Part B, we want T is less than 6. So we would write the symbol T, then the less than symbol, then 6, like so. And for part C, A is greater than or equal to pi. That looks like this. A is greater than or equal to pi. This might seem silly, but the way I was told all sorts of tricks for remembering less than, greater than. The stupid thing that worked for me, and maybe this is because I'm like a millennial and I grew up texting with the T9 thing, this symbol, which everybody used to use as the heart symbol when they text, is less than 3. All right, so if you remember the heart is less than 3, you'll remember that less than is the one that opens to the right, and greater than is the one that opens to the left. If you're someone like me who would mix those up a lot, maybe this is a good way for you to remember it. It worked well for me. The other thing I hear is that the symbol always eats the larger number. So I know that this says T is less than 6 because it's saying 6 is the larger number compared to T because the thing is eating the larger number. Or A is greater than or equal to pi, the thing is eating the larger guy. So A is larger than pi or greater than or equal to. D, this is just stringing these two things together. So I want X to be smaller than 1/7 and also greater than -2. So if I wrote those as separate things, sorry, this is D, not B, D. X is smaller than 1/7, looks like this. And X is greater than, what do we say, -2? -2. So we could write those individually like this, but then observe that this second guy, this is the same. If I tell you Joe is taller than Sally, that's the same thing as saying Sally is shorter than Joe. And then you can string these two together as -2 is less than X is less than 1/7. So that's called a compound inequality, and these are very useful. And then getting to the part that Olivia was asking about, if we look at part E here, we want to say the distance from P to 7 is at most 9. This is a little bit complicated. So the distance from P to 7 is at most 9. This is something that's supposed to be covered in college algebra, but I think it might not be all the time. So the distance between any two real numbers can be expressed as the absolute value of their difference. So the distance from P to 7, that can be written as the absolute value of P minus 7 is at most, we have to translate that into an inequality. Let's see, something is at most 9 if it's smaller than 9 or equal to 9. Can't be bigger than, right? If I say your height is at most 5 feet, then that means you're shorter than 5 feet, right? I'm estimating your height. Your height is clearly no larger than 5 feet. Oh, your height is at most 5 feet. So is at most translates to less than or equal to, and then 9 is of course just 9. So this is the inequality we needed there. So,
what if it were opposite, like P plus 7? How would it be worded instead?
so let's say the distance from X to Y is defined to be the absolute value of X minus Y. So how could you get a P plus 7 there? Well, that would mean maybe I want the distance from P to negative 7. Right, because then I would have absolute value of P minus negative 7. That would give me a P plus 7. So the absolute value of P plus 7 I'll kind of partition this off. That's the same as the absolute value of P minus negative 7. So this would be the distance from P to negative 7. So if you had this algebraic expression, I would interpret it using these words, or these are the words that would lead to this algebraic expression.
Thank you.
Of course, of course. Okay. So I think that handles all the questions from the homework there. If there's anything else that you guys wanted to talk about, you can always send me a Canvas message or come by my office hours. But there is some stuff we need to cover afresh. So today we're going to start on section 2.3. And the title of that section is Information from the Graph. And we've got a few big goals in here. We want to be able to find domain and range. We want to be able to solve equations and inequalities. We want to find intervals of increase and decrease. And I think those are the main things there. Anything else I'm missing? Mins and maxes we can talk about also. Okay. Yeah. So there's really quite a lot here. I'll start with the basics, domain and range. Remember that the domain is the set of all inputs for which we usually use the symbol x. So it's the set of all x values on the graph. And the range, that's the set of all outputs, usually y values. on the graph. So the way I like to think of this is through what I call the squishing game. Suppose I have some function and it's just defined from like here to here. So I'll call this A and I'll call this B. This is the graph y equals f of x. And my pen is starting to die. Surely I have another good pen here somewhere. So to find the domain, I squish everything down onto the x-axis. So I would project this whole graph down onto the x-axis, and I'll find that my domain here would be this interval, the closed interval from A to B. And to find my range, so this is the domain, I would need to squish everything onto the y-axis. So I imagine that all these points on the graph, they can't move up or down, but they can move left or right, and I just smush them over until they're sitting right on top of the y-axis. The smallest point in my domain, or sorry, the smallest point in my range here isn't coming from this, it's coming from this down here. And the largest point in my domain is coming from this over here. So if I call this y interval the interval from C to D, then my range is just that. Now I know you guys have been beaten over the head with domains and ranges since, early algebra classes, and I don't want to beat you over the head any more than is necessary. So maybe we'll look at one explicit example here. And these guys here are filled in. So if this is the graph y equals f of x, this is the x-axis. If I were to smush this whole graph down onto the x-axis, the two will get hit. This point, for example, would come down here. Everybody in between 2 and 4 gets hit, including the 2 and the 4 themselves. So the domain is the closed interval from 2 to 4. On the other hand, if I was to smush everybody over here until they're piled up onto the y-axis, I would need to know what this y value up here is. This appears to be a circle of diameter 2, so the radius there would be 1, so this would be 1. And my range would be everybody that gets hit by some point when it all gets smushed over onto the y-axis. So that would be the y interval from 0 to 1. So this smushing game is a really good way to find domains and ranges. If you're ever stuck or you're not sure, you're trying to remember a rule that you used to know, just take a look at the graph and imagine smashing it onto the x-axis for the domain, onto the y-axis for the range. the next thing we wanted to talk about how to find after domains and ranges is solving equations and inequalities. This is a big deal. So we want to learn how to solve equations and inequalities just using the graph. For this, it would be really nice if I had two colors. So let me pop a fresh purple thing in my G2 here, and we can use purple and black. I know the colors don't come across beautifully on the document camera, but I'll do my best for you. Make sure this is writing. Okay. So in black, I'll draw the function f. And in purple, I'll draw the function g. Now maybe this is x equals 1, 2, 3, 4, 5, 6, and 7 here. If I wanted to solve the inequality, well, let's start with the equation. To solve the equation, f of x equals g of x. Remember, these guys are outputs, they're y values. And they depend on the inputs, the x values. So we're asking for what x values do the y values on the graph match? That's equivalent to asking solve the equation f of x equals g of x. If you have an x value at which the y values match, then the two graphs have to go through the same point. Above that x value, if the y values are the same, then that point is on the graph of g of x and on the graph of f of x. So another way to say this is find the x values where the graphs intersect. So for this example, f of x and g of x are equal to each other if and only if x is 1 or 7. And the solutions to an equation like f of x equals g of x always going to be x values. Questions on this concept? Solving these equations graphically being the same as finding the x values of the intersection points? Okay. What about an inequality then? So I'll stick with the same picture. I want to solve the inequality f of x is greater than or equal to g of x. This is the same as answering the question, for what x values is the graph of f, the y values here, for what x values is the graph of f greater than the graph of g? Well, if the output of f is greater than the output of g at a particular x value, that means that the point on the graph of f has to be above the point on the graph of g. So we're asking for what x values, remember answer here always x values, is the graph of f above the graph of g. That's the equivalent question. So we're going to find an interval here. If I look, the graph of f is the black graph, the graph of g is the purple graph. Certainly between -1 and 7, the graph of f is above the graph of g. If I take any particular x value in here, the graph of f will be above the graph of g. So here, our answer would be the closed interval from -1 to 7. I use closed intervals because at the endpoints, the inequality is satisfied because it's greater than or equal to. At these endpoints, remember, that's where f is equal to g. It's right at those intersection points. So greater than or equal to will usually correspond to a closed interval. Similarly, the solution to f of x is strictly greater than g of x would be anywhere in between 1 and 7, but not 1 and 7 themselves. So that would be the open interval from 1 to 7. So weak inequalities, the greater than or equal to, the or equal to part, we call that a weak inequality. It's not a strict inequality. It doesn't have to be strictly greater than. It's allowed to be greater than or equal to, which is a less strict requirement. So we use the word weak there. Weak inequalities like this usually have solutions that are closed intervals like this. And strict inequalities like this usually have solutions that are open intervals like this. That's always true as long as your functions are continuous. If you have a function that's discontinuous, then those little rules of thumb don't necessarily work. So here 1, 7 closed is the solution to the weak inequality, where is f greater than g. And 1, 7 open is the solution to the strict inequality, where is f strictly greater than g. So let's do an example or two here. Let's do a concrete example. Let's solve several inequalities relating, equations and inequalities relating the functions f of x, and for f I'll use about 2x squared plus 3. Sorry, looking over at my notes. And g of x, I'll use 5x plus 6. I want to solve f of x equals g of x. F of x is greater than g of x. Let's do f of x is less than or equal to g of x. And then we'll do the greater than as a part C. Remember, this guy is equivalent to, if I actually plugged in, I could have asked you the question as 2x squared plus 3 is equal to 5x plus 6. This one I could have asked as 2x squared plus 3 is less than or equal to 5x plus 6. This guy I could have asked as 2x squared plus 3 is strictly greater than 5x plus 6. So I could give it to you just like this. I could ask you just straight up solve these inequalities. That would be kosher without ever telling you one of them is f and one of them is g. But I'm trying to help you see it in terms of the pictures we've been drawing. So maybe imagine the problem was given to you just as this. What would we do? I would identify one of them as f and one of them as g, and I would draw the graphs. So let's do that. 2x squared plus 3. That's a parabola who opens up and has his vertex at 0, 3. So I'll take this 1, 2, 3. And here is my parabola, 2x squared plus 3. It doesn't have to be perfect. And 5x plus 6, let's see, 4, 5, 6, is a line with a pretty steep slope, looking like this. So this is g of x, this is f of x. And if I wanted you to do this graphically, I would need to give you a little bit more information. I would need to tell you what those intersection points are. Of course, you could find them by solving this, but I'll tell you for now, because we're just trying to practice doing this graphically, this intersection point here is at -1. And the other fellow over there, where the fuck is he? 1, 3. Okay. So if I wanted to solve the inequality, or first say solve the equation, f of x is equal to g of x, graphically, I wanted to solve this equation just using this graph, what would I find? Remember, this is the same as asking, where do these two graphs intersect?
At -1 and 3.
Yeah, so this first guy has solution x equals -1 or x equals +3. What about this first inequality? I want to know, where is 2x squared plus 3 less than or equal to 5x plus 6? I want to know, where is f less than or equal to g, where f is this parabola and g is this line. So I'm looking for places where the parabola is beneath the line. Oh, jeez. Can't do that, dude. Sorry, not you. Well, if I look like right here, for example, the parabola is beneath the line at this x value, at this x value, at this x value, at all the x values between -1 and 3. And they're actually equal to each other at 3 and at -1. So the solution set here is the closed interval from -1 to 3. Closed interval because less than or equal to, so them being equal is okay, and we know they're equal at -1 and at 3. Are we all comfy with why this is the solution to this inequality? And problems like this, I assure you, will show up on an exam at some point. Okay, we're awful quiet there. Who can help me with this last piece? Yeah, Austin's got it. So we want to ask, where is the parabola above the line? Certainly everywhere to the left of -1. If we look anywhere over here, that line continues down and that parabola continues up. So the parabola is above the line everywhere to the left of -1. So that's the interval -infinity to -1, and we use an open interval. We always use open on the infinity symbol. We use an open at the -1 because at -1, this isn't strictly bigger than this. This is exactly equal to this. And I want to know, where is this bigger than that? And then we're going to have to union this with the other place where f is above g. If these continue like this trend, as we're seeing here, f is above g everywhere to the right of 3. So I would union that with 3 to infinity. So the open interval from -1 to 3 is the solution to an inequality we haven't written down. That's the solution to the inequality like this, but without the or equals to. So if I asked you, where is f strictly less than g, that would be the open interval from -1 to 3. But here we're asking kind of the converse to that. Where is f bigger than g? Where is the parabola above the line? And the parabola is above the line as long as x comes from this set. Is that clear? Okay, cool. Yeah, I would think of, for that last guy, I think of kind of sketching my solution interval down here. And that'll remind me, oh yeah, I've got to go out to infinity on both sides. So the shaded region on the x-axis there is the solution to the last inequality. And then when we write that in interval notation, it looks like this. Okay, so solving inequalities and equations graphically is not terribly hard, but you need the graph. That's the big starting point there. So again, those graphing skills that we've picked up in previous algebra classes are very important. If we weren't given these intersection points at the start, we would have to solve for them by solving this quadratic equation, which would require some factoring. So you might want to remind yourself how to do that. But for now, we're focusing on just getting the information from the graph. Last call for questions about any of these three. Okay, we have a few minutes left, and in these last few minutes, I'm going to discuss what it means for a function to be increasing and what it means for a function to be decreasing. I know you've seen this in college algebra or high school classes, but there's a little difference between how we do that in those classes and how we do that in pre-calc. So first, let me Let me remind you what the picture looks like from the college algebra perspective. And here's my function f. And I'm going to label a few points here. I'll call this a. And I'll call this x value here b. In college algebra, we say, you know, imagine a little dude walking along the graph. He always goes left to right, and he's always glued onto the graph. He can't jump up or fall beneath it. Think of the graph as like a pathway that he's walking along. If as you go left to right, so this is the college algebra, definition for increasing. Say if as you walk left to right along the graph of f of x, you are going uphill, we say f is increasing. So this is something that happens on open intervals. For example, right here at this point, where I turn from going uphill to going downhill, I can't say whether I'm going uphill or downhill at that point. In fact, I'm doing neither. So here, I would say I'm definitely increasing from negative infinity. So we always respond to these. The answer to these are always, I should write this in big bold letters, always open intervals of x values. People get especially confused with the x values part. We're not looking for points, and I'm never going to be asking or wanting y values as the answer to where are we increasing or where are we decreasing. It's always open intervals of x values. And similarly, the college algebra of decreasing we would say if as you go or as you walk left to right along the graph of f of x, you are going downhill. Then we say f of x is decreasing. So certainly everywhere over here, as I go left to right, I'm going uphill. And then I turn around and I start going downhill. And then I turn around again and start going uphill. So here I would say that this function, if this, I call this guy f of x, here, f of x is increasing on the interval negative infinity up to a, because remember it's always x values. I don't give a shit what the y value is. So from all the way out here along my x-axis, from negative infinity all the way up to a, my dude will be going uphill. And then also from b to infinity. And f of x is decreasing on the interval a to b. A word of warning. This looks a lot like the ordered pair a comma b, but it's not. It's the exact same notation that we use for the ordered pair A comma B, but it's an open interval. And it's always a good idea to write the interval so that you know, to remind yourself, to never put any y values. These are all x values, always open intervals of x values. The whole reason the definition of a function is what it is, right? Where every input goes to one and only one output, the vertical line test, the whole reason for that is so that we can describe the behavior of a function purely in terms of its x values, because there's guaranteed to only be one x value above b. Otherwise, this thing wouldn't be a function. So you can tell me where I am on the graph just by telling me the x value, and that's the point. So we always, always, always refer to locations, places shit is happening, like increasing, decreasing, mins, max, whatever, locations. The answer to any question that begins with the word where is always x values. Where is f increasing? Oh, on the interval of x values, negative infinity to a, comma, b to infinity. Where is f of x decreasing? On the interval a to b. And these are always, always, always x values. The last thing I'm going to leave you with here is the slightly more grown-up definition. And we'll see that these coincide. The function f of x is said to be increasing on the interval a to b if for every x1 and x2 in the interval ab with x2 greater than x1, f of x2 is bigger than f of x1. There's a lot of words there, but the result is a more rigorous definition. So if you want to say the function is increasing everywhere on this interval, you have to be able to say, well, if you go further to the right, if x2 is bigger than x1, then you have to be going uphill. F of x2 has to be bigger than f of x1. So here's the picture. Let's do it like this. So here's B, here's A. If I take any two x values in here, x1 and x2, this point right here is x2 comma f of x2. This point right here is x1 comma f of x1. And what you notice is that the y value, f of x2, is bigger than the y value, f of x1. So it's the same definition, but it's a little bit more rigorous. You can actually deduce from this definition that the intervals of increase and decrease must be open, at least for continuous functions. So if you take any two x values in the interval AB, with x2 being larger than x1, so x2 to the right of x1, then the y value above x2 has to be above the y value at x1. If this is to the right of this, then this must be higher than this. That's what this says. If x2 is to the right of x1, then f of x2 has to be above f of x1. And to get the definition of decreasing, you just turn the inequalities over. Similarly, the function f of x is decreasing on the interval a, b, if for every x1 and x2 with x2 greater than x1, we have f of x2 is smaller than f of x1. So it says if you look to the right, if this guy is to the right of this guy, then his y value has to be below his y value. So if here's A and here's B, I want to say that this function is definitely decreasing from A to B, right? Well, if I take an arbitrary x1 and x2 in that interval, I need to check that the y value at x2 is below the y value at x1. And it is. Here's f of x1, here's f of x2. So these are the slightly more grown-up definitions of increasing and decreasing. But conveniently, it's equivalent to the definition you already know. There may be instances where I rephrase this. I could ask a question, you know, suppose for every x2 bigger than x1, f of x1 is less than f of x2. What could we say about f on the interval from which those x's come? And you would need to be comfy enough with these definitions to deduce what it is we're getting at. Come in a little bit more here. Okay, so questions about these definitions or these pictures? We all feel fairly comfy? So my one caution here, the one thing I'd like to remind you before we vamos for the day, is that increasing and decreasing, the answers are always open intervals of x values. The x values thing is especially important. Don't confuse yourself by trying to throw y values into the answer. Y values are relevant for figuring things out, right? Like where's the graph above the, you know, where are you going up, where are you going down? But your answer is always coming from the x-axis. All right, so this is where we will pick it up then on Wednesday. I will do some examples, explicit examples, where we calculate intervals of increase and decrease. And then we'll see how those connect to the concepts of mins and maxes. We'll define a local min, a local max, and an absolute min and an absolute max. Those are all fairly straightforward. They are what they sound like, but there's some kind of vocab stuff that's a little bit subtle in the same way this is a little bit subtle. And also, we'll have definitions that are a little bit more grown up than the definitions that we're used to from college algebra, and we'll need to be able to parse those to understand those. Lily asked, when's the homework going to be up? So I've got 3 homework sets that I need to review and publish. I don't like just sending them out as they are. I add problems and remove problems. So give me about an hour or so, depending on how busy my office hour is this afternoon. Give me about an hour or so and the homework should be up by then. Alrighty. Okay, I think that's where we're going to wrap it up for the day. Any last minute questions for me, guys?
No, thank you.
Okay, cool.
Thanks.
All right, yeah, take care.
Thank you.
Of course, have a lovely afternoon, and I'll see you, if not in office hours, on Wednesday.